Okay, so Gauss's law. So this is the second portion of chapter number 17. This one is actually fairly straightforward.
In Florida, there's a special lab
It's going to help us
studying lightning. ABC's Bill
understand if you come
Blakemore went to pay a visit.
At any one moment, there are about 2,000 electrical storms on our planet. It's a constantly crackling ball of lightning, about 100 bolts a second, striking people, houses, power lines, airplanes.
All right, so you're inside an airplane. You're perfectly safe. Question is why?
High winds took down a power line.
So you got the live wire going up, touching the metal casing of the car.
Inside her car, police.
And she's perfectly safe. Most of you guys thought that she was safe because of the tires. Of course, the tires got nothing to do with it. In essence, the live wires touching the metal casing and touching the ground, the entire car becomes electrified as a result. So it's part of the circuit. So just having tires will not help you or hurt you. It's nothing to do with it. So the question is, why is she safe as long as she remains on the inside? A lot of you guys, once again, mistaken thought that she wasn't touching the metal inside the car. She wasn't touching any of the metal inside the car. But she can touch all the metal she wants, inside or outside of the car. So it's not going to make any difference. She's still going to be safe. But once again, the question is why. Okay, so
please help me out. Yes, we'll carry you. Hold on. I got struck by lightning. Yes. How the fuck did that happen?
In August 2003, Matt Thompson was hit by lightning in the hills outside Keystone, Colorado.
A bolt of lightning taken straight in the chest. The direct hit traveled all the way through Matt's body.
I had no clue what happened.
Matt's story was big news. On websites worldwide, the issue was raging.
Matt, you almost died.
Was Matt's metal tongue stud the reason he was struck?
So my tongue ring. Oh no, dude, you might have swallowed it. Let me see. Where's your tongue? Let's see it. Oh, it's broken off in there, it looks like.
Body jewelry attracting lightning strikes?
So metal on your body, does it attract lightning? Does metal in general attract lightning? All right, most of you guys will probably say yes to that, but let's just focus on the question. The lightning rods, what's the purpose of the lightning rod? The purpose of the lightning rod is to attract lightning to yourself, right? So the lightning rods, are they made up of wood, plastic, metal? All lightning rods are made up of metal, right? So they make the lightning rods out of metal. Is that because metal is more attractive to lightning? Is that what it is? If so, the metal on your body, will it attract lightning? So these are the questions that we're going to get to explore. Let's talk about Gauss a little bit. So this guy is a German mathematician. In fact, considered to be one of the best mathematicians who ever lived. It was one of Einstein's heroes. Einstein ended up using the sort of mathematics that Gauss developed in developing his own general relativity. General relativity is the theory of gravity that Einstein came up with, and he spent like 10 years working on it. This was fairly challenging and complicated. All right, so in honor of Gauss, obviously they got his picture on their German currency, so this guy's a big deal. One of the contributions that Gauss had is a mathematical method that we will get to use that simplifies physics quite a bit. All right, so Gauss introduced a mathematical concept into physics, otherwise known as flux. All right, so what is flux? So let's talk about flux a little bit. All right, so this is known as the Gauss's law. It's kind of a mathematical simplification of the value of the electric field of any charge distribution that you can imagine. I'm kind of exaggerating a little bit. Well, let me just set it up for you and then we'll have a discussion. All right, so this A represents the area, surface area of something. All right, so I'm just setting up the mathematics for you guys. And the area is a vector, which means that area is going to have a direction, obviously, and whatever that means. I have to give you some kind of a demonstration of it. So area is going to have a size as well as it's going to have a direction. That's what it means. But the best thing to do is just do a visual demonstration of it. All right, guys, this napkin has an area, so it's got a size. Notice that I changed the size of it. Now it's got a bigger area. And also notice that I can actually point this in a way I want. All right, so I can face it this way, I can face it that way. So which means that it also has a direction. So when I turn it this way, area exposed to you looks smaller. This way it looks larger. This way it looks smaller. So it's got, the area has direction. So it's gonna be pointing this way, that way, or that way. Okay, just remember that area is a vector. Not only it's got size, but also it's got direction. So that's what it means. All right, so here's your area vector. It's got size, also it's got direction. So the size and direction is in this, obviously it's pointing in this direction, and then area, A is gonna represent the size of it. Okay, so we treat the area as a vector, and then what we'll do is let's have an electric field pointing in this direction, okay, making an angle with respect to the area. So here's the electric field vector, here's the area vector. So if you take the dot product of the electric field and the area vector, it's gonna give you the flux. All right, so this symbol that you're looking at is the Greek letter F. All right, so it's known as phi or phi, depending upon how you want to pronounce it. Okay, so so far so good. I didn't really say anything that you were able to comprehend. Okay, so I've been talking complete abstraction at this point, trying to describe what Flux came up, what Gauss came up with. Okay, so we came up with the mathematical expression for flux. Okay, so what does flux mean? So flux means flow. That's it. Translated in English, it means flow. It represents the amount of electric field flowing through this area, or the amount of electric field being intercepted by this area. That's it. So whenever you're dealing with flux, you're always dealing with the amount of electric field which is going to be intercepted or flowing through a certain region of space, certain area that you're looking at. All right. The amount of electric field which is flowing through the area is going to depend on the strength of the electric field, the size of the area, and then it's going to depend on the cosine of the angle between the electric field vector and the area vector. So the details aren't that important, but what's important from our purposes is the amount of electric field intercepted by this area is going to depend on the charge, net charge. Q represents the net charge enclosed within a Gaussian enclosure that we will deal with. Okay, so I'll try to provide a better explanation shortly. I'm just setting up the mathematics for you guys. All right, so this sphere phi is going to be your flux, so that's going to represent the flow of the electric field. A is the strength of the electric field, so this is the area of the enclosure that we're going to be looking at. Q is going to represent the net charge within the Gaussian enclosure, whatever that means, it'll make sense. And this epsilon naught is, we've seen this term before, it's a constant, this is the space permittivity constant. All right, so now let me take you through the next slide. Okay, this is where, all right, so the next slide is not that one. All right, so you can see the meaning of it, examples of flux. All right, so it's going to be flow. Number one, every time you're dealing with flux, you're dealing with the electric field generated by a positive charge, negative charge, or whatnot. Okay, so you're always going to be dealing with the amount of electric field going through a Gaussian surface. Okay, so the Gaussian surface is an imaginary surface. It's going to create some kind of an imaginary enclosure where the charge is. Okay, so flux, the flow is going to depend on the net charge within the Gaussian surface that you're looking at. So this is a positive flux, or it's known as the positive flux is an odd flux, or it's more like an odd flow. So what's odd flowing is the electric field. So Gaussian surface is the surface of a Gaussian enclosure. A Gaussian enclosure is just an imaginary area that you're dealing with. So this is not a real thing. Right? So charge is real, the electric field is real. So what we're trying to figure out is the strength of the electric field, which is going to be generated by the charge. So we come up with the concept of flux. So it's, in this case, it's an odd flow, it's an odd flux, or positive flux. So the flux depends on the net charge within the enclosure. So this gives you a positive flux, positive flow. If there's a negative charge, or in this case, you get a negative charge, you get positive and negative charges next to each other. So we will take a look at a couple of cases. So if this is a negative charge, notice that the electric field lines are pointing towards a negative charge. Okay, so now we are going to be interested in the flux of this situation. So we draw our Gaussian enclosure. All right, so it's going to have its imaginary Gaussian surface. And so the flux is going to depend on the net charge within this Gaussian surface. So it's the net charge is going to be negative. So what happens is going to give you a negative flux or negative flow. All right, so now you have two charges next to each other. All right, so one is positive, the other one is negative. So the question is, what is the net charge inside the enclosure, the Gaussian enclosure? So the net charge within the Gaussian enclosure is going to be 0, right? So you got positive charge, you got a negative charge, so they will add up to 0. So the net flux of this is going to be 0. Okay, so also the flux is, remember guys, by definition, the flux is the number of, that's the amount of electric field. So the number of electric field lines intercepted by the Gaussian surface. Notice that the number of lines leaving the Gaussian surface and entering the Gaussian surface will be equal to each other. So that's also going to give you a 0 flux. That's what it means. So now if you're interested in the flux within this region, all right, so you got a negative charge here. If you're interested in the flux within this region, what is the net charge within this region? So you got absolutely no net charge within this region. So as a result, what happens? The flux is going to be 0. All right, so that's the meaning of flux, guys. Flux means flow. Positive charge is going to give you a positive flux. Negative charge is going to give you a negative flux. Positive charge is going to give you a positive flow, odd flow. Negative charge is going to give you a negative flux, negative flow, inflow. So which means that the electric field is going to be pointing in towards this region. No flux means the net charge within the Gaussian region is going to be 0. It doesn't mean that you don't have any charges, the net charge is 0. Or sometimes you don't have any charges, which means that the flux is still going to be 0. All right, so that's a quick introduction. All right, so we're looking at a region. All right, you got a negative charge, you got a positive charge, you got no charges here. All right, so S1 is going to be your first Gaussian surface. So if you look at the first Gaussian surface of the first Gaussian region, within this region, the Gaussian region, what do you have? So you got positive charge, so this is going to be a positive flux. So this is going to be an outflow. So if you end up getting a positive flux here, this region, net charge is going to be negative, so you end up getting a negative flux. This region, right? You got no net charge on the inside, so it's going to be 0 flux. S4 is going to represent the fourth region. So what do you have within the fourth region? So if you make this your region encompassing everything else, all right, so you get positive charge, you get negative charge, so the net charge is going to be 0, so your net flux is going to be 0. So this is going to be your 0 flux. All right, so that's a powerful concept. How so? Let me show you something. Coulomb's law. All right, so remember we came up with an expression for the strength of the electric field for a point charge. So I just want to show you that you can come up with the same thing by using the Gauss Law. All right, so I gotta just wait for a second. PowerPoint is trying to catch up. Okay, so this is a simple example of it. So you got a point charge. Let's assume that you want to know the strength of the electric field generated by a point charge. Okay, so E, this is my point charge. I want to come up with a mathematical expression for the strength of the electric field for a point charge. Okay, so Gauss's law is a simplification. It's just a mathematical trick that allows you to be able to figure out the strength of the electric field of usually symmetric distribution patterns. All right, so Flux equation looks like this. All right, so flux is the amount of electric field which is going to be intercepted by the area of the Gaussian surface. So that's the area of the Gaussian surface that you're looking at. So green stuff is the area. This is your Gaussian region. So which flux depends on the net charge inside the enclosure of the Gaussian surface. All right. So what I'm going to do is I'm going to solve this for E. So this is the expression of the formula. So get rid of the area. All right, so it gives me a nice little expression. Now I have to come up with an expression for the area of the Gaussian surface. So the enclosure, the imaginary enclosure that I'm looking at, two-dimensional looks like a circle, but obviously I'm enclosing the charge in a three-dimensional space, so that's going to be a sphere, right? So enclosure is going to be spherical, so area of a sphere is what I'm interested in. So area of the sphere is going to be 4 pi r squared, so r is the radius of it. So you do a back substitution into that formula, and then you end up getting an expression that looks like this, all right? So what I'm going to do is I'm going to clean this up. All right, so I'm going to take 4 pi and then epsilon naught. These are my constants. I'm going to just put them to this side, and the rest is going to be q divided by r squared. Okay, guys, you will recognize this expression 1 over 4 pi epsilon naught. This was the strength of the electrostatic force. All right, we saw this expression before. So you do a back substitution. When you do a back substitution, you end up getting the strength of the electrostatic force for a point charge. Okay, so the Gauss's law is a bit of a mathematical trick. Once again, if you're interested in the strength of the electric field due to any symmetric distribution patterns, it works. Okay, this is not something worth memorizing. I just wanted to show you a demonstration of it. All right, so it's this Gaussian region. It's just an imaginary region that you draw around a charge or charge distribution that you're interested in. It's usually, so flux is the amount of electric field which is going to be intercepted by the area of the Gaussian region. In this case, charge is assumed to be, point charge is spherical, so obviously the Gaussian region is also going to be spherical, so you just get the area of that region. All right, so going forward. Okay, so for our purposes, this is going to help us understand quite a few stuff.
As Apollo disappeared beyond the clouds, Commander Pete Conrad reported catastrophic failures to the electrical systems.
Yeah, the problems here. I don't know what happened. I'm not sure you can get by lightning.
Conrad was right. These photographs reveal that it was struck, not once, but twice, by lightning that came seemingly from nowhere. Quick thinking by Mission Control helped them restore power, but it was a close call.
We've had a couple of cardiac arrests down here, too, Pete. I think we need to do a little more all-weather existing. Amen.
It was a problem that needed urgent attention. NASA dispatched test pilots to seek out thunderstorms. Their missions took them through turbulence and hailstones, which could tear a jumbo jet apart.
One of the very early strikes that we had, where it struck the nose boom, as many of our lightning strikes did, and it then swept up over the top of the windshield, down that metal bar that was over the top of our heads in the canopy. And I could just happen to look up, and I could see helical chunks of plasma as the lightning channel broke apart as it flew back over the top of my head.
The onboard camera revealed something totally unexpected. The plane wasn't just intercepting lightning, it was actually triggering it by interfering with the electrical field inside the cloud. As Apollo 12 flew through the cloud of charged ice particles, it left a wake of hot ionized gases and conductive contaminants. The exhaust became a huge streamer, and the burning rocket plasma a giant lightning rod.
All right, so the question is,
Took them through turbulence and hailstones.
why is it that you're safe inside an airplane while it's being struck by lightning? All right, here's the reason why. Okay, so when there's lightning, what happens, the lightning is going to transfer light charges to the airplane. So every time the lightning strikes, the negative charges or positive charges, in this case, the negative charges are the ones that are going to get transferred to the airplane. So it deposits the light charges. Remember, the airplane's made up of metal. It contains equal number of positive and negative charges, so that the airplanes are neutral. So when you actually charge them up negatively or positively, what happens to the light charges? Light charges will be repelled to the surface. So the charges are going to try to get away from each other. as far away from each other as possible. The furthest that they could get away is going to be the surface. So the like charges will be repelled to the surface immediately. So the surface becomes either positive or negatively charged. In this case, it becomes negatively charged. All right, so here's what happens when there's lightning. All right, so when there's lightning, so surface is going to become, in this case, in our case, it's going to become negatively charged. So this is a hollow conductor. A case in point, it could be an airplane, so I don't have a particular shape. It could be a car. And through lightning, you end up depositing negative charges. So which means that the metal is going to become positive or negatively charged. Doesn't matter, metal's not conductor, so the like charges will try to get away from each other, as far away from each other as possible. The furthest that they can get away is going to be the surface. So what happens, immediately this net charge is going to go to the surface, so the surface is going to become charged. All right, so the surface is going to be charged. So the surface is going to be negatively charged in this case. All right, so if that's the case, what's the net charge on the inside? Guys, the net charge on the inside is 0. The like charges cannot penetrate into a hollow conductor, all right? So which means that the like charges will be repelled to the surface becomes charged. The inside of it, there's not going to be any net charge. All right, so the green represents my Gaussian region. Remember, this is three-dimensional, all right? So let's try to figure out the strength of the electric field on the inside this hollow conductor. Airplane, car, I don't care. It's just a metallic enclosure. So what is the strength of the electric field on the inside? And this is the reason why the Gauss Law is amazing. So now we can actually come up with an expression. So we have an expression for flux. According to flux is the amount of electric field which is going to be intercepted by the area of the Gaussian region. So the amount of electric field intercepted by the area of the Gaussian region depends on the net charge on the inside. So for E, all right, so this is going to represent the electric field intercepted by the Gaussian region due to the net charge on the inside. So what's the net charge on the inside? Guys, it's going to be 0. There's no net charge on the inside. Right, the excess charge is going to be repelled to the surface, so net charge on the inside is going to be 0. Because the net charge on the inside is 0, the electric field on the inside is going to be 0. So which means that there's no electric field on the inside. So what does it mean from your perspective? Guys, the electric field is what forces charges to go through your body. The electric field is an electrostatic force field. If there are charges inside the enclosure, those charges are going to be pushed this way or that way. Positive charges are going to get pushed in the direction of the electric field, and negative charges will be pulled in the opposite direction of the electric field. So which means that there will be currents, which means that you will get, potentially you will get shocked. But because there's no electric field on the inside, there's absolutely no reason for you to get shocked. You can touch the inside of the metal, you're fine. You can put your face next to the metal, you're fine. You can lick the metal, you're fine. All right, you're not going to get shocked inside a metallic enclosure. This is otherwise known as the Faraday cage. Net electric field on the inside is 0 because the net charge on the inside is 0. All the excess charge is going to reside outside. All right, so the charges deposited by lightning, in this case, the negative charges, will get repelled to the surface. They will get pushed to the surface, so the net charge is going to reside outside. So you draw your Gaussian surface, all right, and then take a look at the flux. Flux represents the amount of electric field intercepted by the Gaussian surface that depends on the net charge on the inside. And guess what? There's no net charge on the inside. The net charge is on the outside. If the net charge on the inside is 0, there's no electric field. If there's no electric field, you cannot get shocked inside the surface, inside the inside the enclosure, Gaussian enclosure, otherwise known as the Faraday cage. So excess charge is going to remain on the outside of a conductor. It's going to remain at the surface of a conductor is a better way of saying it. So none of the excess charge is going to be on the inside. So which means that there's no electric field on the inside. So which means that there's no force field on the inside. That's going to force the charges to go through your body. So as long as you remain inside a metallic enclosure, you're going to be 100% safe. All right, so here's a laboratory environment. So they generate a spark, a minute of lightning, and notice that the person is on the inside. The person is perfectly safe. What's happening is the lightning is going to the ground through the tires. So tires will not help in the circumstances.
You can't do that. You should get into a metal car.
The car's metal body discharges the current away from the driver and below.
All right, so any sort of metallic enclosure is just about to be the safest place where you could be during a lightning storm. Inside an airplane, inside a car. Absolutely. All right, so pick out the best answer, put it in your, put the best answer in the chat. All right, just about every single person got it right. So these are the best answers. So inside any sort of metallic enclosure is the best place to be. All right, now that you know the answer.
True or false? You can be electrocuted by lightning in your car.
All right, true or false? You know, that's false, right? It's 100% false. All right.
The answer is true.
Oh, the answer is true, evidently. Okay, so now this got my attention. So I know from physics that you should be fine inside a car. Okay, It's a metallic enclosure. I explained the reasons as to why you're going to be 100% safe as long as you're on the inside. Except
By light.
this guy says, or at least this program is TLC, teaching and learning channel used to be, I don't know if it still exists, 10 to 11 carrier channel it became. At some point they stopped doing science because they weren't doing a good job in the first place. And this is the demonstration of it. I recorded this like 20 years ago.
In your car. The answer is true.
All right, so almost created the impression that they actually
Watch.
caught someone getting struck by lightning while driving.
You're about to see actual video of what it would look and feel like if it happened to you.
Ah! Oh my God! The car was just struck by lightning! Oh my God!
This young man from Colorado was lucky not to be electrocuted. The outer surface of his car took a hit, blowing out his tires as the lightning sliced through his car and into the ground.
What happened was that it hit the radio antenna. It used to be right here. Big antenna going up about that high.
If you find yourself driving through a lightning storm, pull over and keep your hands on your lap. Don't touch metal like the steering wheel or the radio. That way, you'll survive this.
All right, so let's go back and clean this up a little bit.
Of what it would look and feel like if it happened to you in your car. You can be electrocuted by lightning in your car.
He didn't get electrocuted by lightning in his car.
The answer is true.
The only demonstration I've seen so far, the evidence is the answer is false. Your car can get struck by lightning. That's the only thing that they proved after this
Watch.
point.
You're about to see
So the car gets struck by
actual
lightning.
video of what it would look and feel like
By the way, this guy is a storm chaser.
if it happened to you.
He startled, nothing happened to him. Windshields are working, so the electrical system is fine.
God! The car was just
Engine is still running, so engine is fine.
lightning! Oh my God!
This young
You can see the clock, so the electronics is fine. So just like I said, the charges did not penetrate into the metal. So this is a hollow metal. It's a metallic enclosure. None of the charges penetrate into the
man from Colorado was lucky not to be electrocuted.
It's got nothing to do with light.
The outer surface of his car took the hit,
It was inside a metallic enclosure. That's the reason why it was fairly safe.
blowing out his tires
Tires didn't help.
as the lightning sliced through his car and into the ground.
What happened was that it hit the radio antenna.
So the antenna ended up attracting the lightning. The antenna acted like a lightning rod. It vaporized, completely
It used to be
vaporized.
right here. Big antenna going up about that high.
If you find yourself driving through a lightning storm, pull over and keep your hands on your lap.
All right, guys, that's nonsense. You can touch all the metal on the inside. It was touching the steering wheel. It was
Don't
fine.
touch metal like the steering wheel
You can touch all the metal on the inside. Makes no difference. You're going to be 100%
or the
fine.
radio. That way, you'll survive this.
All right, hence the reason why TLC stopped doing science after a few years. It was complete nonsense. This is from TLC, but this one is good. There's a reason for it.
The monster created by a man they called Mad is turned loose to strike terror into the hearts of men.
Austin Richards is a self-described mad scientist. But tonight, he's going to play both Dr. Frankenstein and the monster at the same time. He plans to zap himself with 2 million volts of electricity, protected only by a homemade metal suit.
I've really been obsessed with the idea of being a mad scientist. The mad scientist knows exactly what he's doing, but at the same time, there's sort of an element of unpredictability to what he's doing. Sometimes it gets out of hand.
Austin's interest in current events began when he was 14 years old. For a Halloween show, he built what's known as a Tesla coil, a machine that shoots fiery bolts of electricity through the air.
And that first Tesla coil made sparks that were about 12 inches long.
Tonight, Austin is unveiling his latest creation, 2 giant Tesla coils that can fire 2 million volts over 20 feet. He isn't satisfied with just watching this dangerous light show. He wants to be part of it. Austin knows he could never survive a direct hit from the giant coils without some sort of protection. So he designed a special suit made of metal that would transform him into a human lightning rod. The idea for the suit first came to him at a restaurant, and he quickly scribbled his original design on a napkin. Eager to bring his creation to life, he went shopping for parts at the local hardware store.
So I started selecting bits and pieces of heating duct and dryer duct, actually trying them on my body, slipping them on my arms and legs, and I got some interesting comments from some of the people that work there.
That makeshift suit has now evolved into this, makeshift suit. And though he may not make any best dressed lists, Austin hopes his suit will protect him from a 2 million volt direct hit.
What we're going to try is something that's never been tried before, which is to create almost, in a sense, double jeopardy, having 2 Tesla coils, suffusing a whole area with electricity, and I'm going to put myself right in the middle of it.
Austin has invited a select group of guests to witness his terrifying experiment. But are they going to see an electrifying performance or an electrocution? Austin begins by displaying the awesome power of the giant Tesla coils. He holds up a block of wood. It bursts into flames, but he's shielded by his protective glove. So far, so good. Next, Austin ups the stakes by raising up a solid steel wrench. It's bombarded by a barrage of bolts, but he's still okay.
Now he's going to step right into this electrical storm and subject himself to 2 million volts of white-hot lightning. This scientist must be mad. If Austin's homemade suit should fail, he could be fried to a crisp.
If I haven't done my safety check properly, I could die.
He cautiously moves into position. The coils surge to life. Millions of volts of raw power pound his body. The shocked onlookers can't believe what they're seeing. It only takes 100 volts to kill someone. So how could Austin survive 2 million? Incredibly, he's done it. Austin's electrifying experiment is a success.
I was really hoping that was going to work, in the sense that I was really hoping I wasn't going to get killed or injured. And I remember feeling a really deep sense of relief when the arcs began hitting and I didn't feel a thing.
Beaming with success, Austin lights a cigar to celebrate. His crazy homemade suit actually works. Maybe this mad scientist isn't so mad after all.
It's alive! It's alive! All right, here's a question for you.
Sense of relief when the arcs began hitting.
If you knew that you were about to be struck by lightning, and if you were to jump, would that prevent you from getting struck? The answer to that question is no, right? You still get struck by lightning. All right, so being grounded or not being grounded is not going to make that much of a difference in reality. This guy made it sound like he was in some kind of danger. Of course, he knew that he wasn't. This guy has a PhD in physics. He knows his stuff. For as long as you remain inside a metallic enclosure, you're 100% safe. This is inside a metallic enclosure is the best place to be during a lightning storm. All right, so pick out the best answer. Okay, I guess you got it. All right, very good. This is from one of the conspiracy theories that suggested that we've never been to the moon. How would you survive the radiation out in space? So this is how you survive radiation out in space. If you're worried about the radiation from charged particles, this is how you block the charged particles. Outside of the rocket is metal, and that's part of the reason why. So which means that the net charge is going to remain outside. As long as you're inside, you're perfectly safe. C is the best answer for that one. All right, so the net charge, the excess charge is going to remain on the surface of a conductor. Electric field on the inside is going to be 0. All right, so the conductor is going to shield any charge within it from electric fields created outside the conductor. All right, so what that means is if you have any sort of sensitive electronics, you always have to put them inside a metallic enclosure. All right, as a case in point, okay, so you got the cell phone. Cell phone is going to be inside a metallic enclosure. Your computer is inside a metallic enclosure. So any sort of sensitive electronics, because you don't want to zap it from outside and destroy the electronics, you will always have to put them inside metallic enclosures. All right, so in that way, you're protecting any net charge inside from any sort of outside interferences.
When a thunderstorm forms, people's lives can be at risk.
We tell people when thunder roars, go indoors. What we mean is seek a safer shelter.
If you're ever caught out in a thunderstorm, one of the safest places to be is in a closed vehicle.
Many people believe the rubber tires on a car will keep them safe, but that's not true. It's the car's metal body that provides protection, as this high-voltage experiment will demonstrate. A Tesla coil is the lightning simulator, an electrical transformer that discharges 750,000 volts of electricity, more than enough to kill. Dr. Lisa Lazarek is an electrical engineer who's willing to sit in a car underneath the coil to prove that the metal body will protect her.
The electrical charge striking this car is going to conduct around the outside surface of the enclosed body, so I should be fine as long as I don't touch the metal of the car. But it's one thing to talk about the theory, and it's another thing to put it into practice. So I guess I'm ready.
The electrical charge flows around the metal body of the car and discharges harmlessly to the ground.
I'm fine. The theory has worked as expected. My feet are slightly tingling, and because I was nervous, my hands are still clamped together. But other than that, I'm fine.
Okay, so did you guys see anything wrong with our explanation? Yes or no? All right, guys, now we're done with TLC. Let's move on to Discovery Channel.
Voltage experiment transformer that discharges. Sit in a car underneath the coil to prove that the metal body will protect her.
The electrical charge striking this car is going to conduct around the outside surface of the enclosed body, so I should be fine as long as I don't touch the metal of the car. But it's one thing to talk about the theory, and it's another thing to put it into practice. So I guess...
So it doesn't matter if he touches the metal, right?
Give yourself 10 points. Absolutely right. Okay, so what did we learn? She has a PhD in electrical engineering. Engineering is applied physics. And this is what happens if you don't get the concept. Right? There's no such thing as doing this stuff mathematically. And when you do it mathematically without reasoning or understanding of what you're doing, you don't really learn a lot. You can solve problems, but what exactly do you understand about nature? Nothing. All right, so the way to do it is you use mathematics as an exploration device.
I'm ready.
So what do we know from the math of Gauss's law? Okay, the net charge is going to be on the outside. You can touch all the metal on the inside. She almost gave herself a heart attack.
Fine.
You can touch the metal on the inside. It makes no
As long
difference.
as I don't touch the metal.
Guys, you can touch the metal on the inside. Believe it or not, as you will find out next week, you can also touch the metal on the outside. You'll still be fine. Okay, when you stick your hand out, though, make sure that it doesn't struck your hand. If it does struck your hand, obviously it's going to shock you. Right?
But it's one.
If it strikes the car, not your hand directly, you're still going to be fine. You can touch the metal inside, outside. So the question is, if you touch the metal outside, how come you're still fine? So that's a discussion for next week. This week, just know that the net charge is outside. Okay, charges will not penetrate into the metal. There's no electric field inside the enclosure, so you're not going to get shocked. There's no reason for the charges to travel through
One
your body.
thing to talk about the theory, and it's another thing to.
All right, so Discovery Channel is still better than TLC, but she's not Nova quality. PBS Nova does the best. They got the best of the best scientists. This is more of a physics thing. I would have liked it if they just brought a physicist in, as opposed to an engineer. All right, so speaking of lightning.
Basically, you have a...
All right, so we've seen this one. Okay, a couple of things that I need to focus on. Number one, I kept saying that the Earth is negatively charged, right, initially. So how do we know that the Earth is negatively charged? All right, so Earth is, okay, this is something that we will discuss later. All right, so here's how we know that. All right, so here's the Earth, problem number 7 from the handout. Okay, so I'm gonna go over problems 6 and 7. Okay, so when you're studying for the test, look over these problems. These are relatively easy problems. All right, these are not complicated. So what do we know? When we measure the strength of the electric field near the surface of the Earth, we know that it's got this value, it's 150 newtons per coulomb. It's directed downward. All right, because it is directed downward, that means that the Earth is negatively charged. How do I know that? We'll talk about it shortly. All right, so the question is, what's the net charge of the Earth? All right, so we will make the assumption that the Earth is going to act like a conductor with the uniform charge density. Okay. All right, so here's the problem. So the Earth is this, and we know that the surface is negatively charged because the electric field always points towards the negative charge. That's it. So the Earth's electric field points towards the Earth itself. That implies that the Earth is going to be negatively charged. All right, so I'm going to draw my Gaussian surface exactly just near the surface of the Earth. So green is going to be my Gaussian surface. This is the radius of the Earth. So, and then we're going to try to figure out the strength. We're going to try to figure out the net charge of the Earth. What is the net charge of the Earth in this case? Oh, I kind of messed it up a little bit. We're supposed to put the Gaussian above the net charge. Okay, all right. I have to redraw this. Okay, so I need to place my Gaussian above the surface so that there's a net charge on the inside. Okay, so go along with the explanation. All right, so electric field is a vector pointing towards in the downward direction. So this is going to be negative. A is pointing in the upward direction, so this is going to be positive. So if you got two vectors pointing in opposite directions, when you multiply them, you're going to end up getting a negative expression. So two vectors multiply together to direct, because they are in opposite directions, the expression is going to be a negative expression. From here, you can isolate Q. All right, so you got the strength of the electric field, which is 150 newtons. Area, this is going to be the area of a sphere, area of the Earth that you're looking at. It's going to be 4 pi r squared. So back substitution is what you need. And then clean up the expression. I like to keep my constants pi and epsilon next to each other. So 4 is a constant. So E and R are measure values. Okay, R here is the radius of the Earth. All right, so it gives you an expression. So from this, we know that the Earth is negatively charged. All right, numbers aren't that important. The only thing which is important is how do we know that the Earth is negatively charged? This is how you know. By using the Gauss law, you can actually figure out the net charge, and that's pretty much it. All right, so and then the problem number 6 is related to, remember, the surface is going to become positively charged because of polarization. All right, so initial separation of the charges. After that, the top of the clouds become positively charged, the bottom becomes negatively charged. The surface of the Earth is initially negatively charged. Through polarization, it becomes positively charged. When the electric field strength reaches, it's going to say 3 million, it should be 10,000 meters per coulomb. That's when the lightning is formed. So the question is, if you're looking at an area of like 1 square mile area, okay, so what would be the positive net charge within that region? All right, so how do you do a problem like that? All right, so we do the conversions to metric units. All right, so imagine that this is the area of that region. So what is the net positive charge within that region that you're looking at? All right, so once again, you end up using the Gauss Law. All right, so that's the amount of electric field which is going to be intercepted by that imaginary area that you were looking at, which is the size of square miles. So, okay, so this becomes the active portion of the formula. So it's nicely Q from there. And then just plug the numbers in. It's just going to give you a number. Okay, so the number itself is not that important. It's the method of solving a problem. It's a little bit more interesting. Okay.
Here, Dr. Jeff McHargue is using a super slow motion camera to capture lightning.
Okay, so we talked about capturing lightning. This is not the best example. All right, speaking of lightning.
Over.
Okay, a couple of things. Okay, let me just back out of this one. All right, this is not going to play. I'm fine with that. Does metal on your body attract lightning?
Overcoming the damaging effects of one lightning strike can be hard enough. But a few rare individuals, like Park Ranger Roy Sullivan, are proof that lightning can strike twice and more. His daughter remembers his first strike.
This is from the first one. That's in 42. And lightning went through his watch. You can see it has a hole through side to side.
For 27 years after this first strike, Roy was untroubled by lightning until one fateful day in 1969. A side flash bounced into his truck, hitting him in the neck and burning his head.
Okay, now let's start to clarify some of this stuff. Can you get struck by lightning inside a car? The answer to that question is absolutely you can.
Until one
if the windows are down,
fateful day in 1969.
You're inviting lightning.
69.
Under circumstances, guys, your body is going to become polarized. Right? Your top of your body is going to become positively charged. Your body becomes polarized. So make sure that if your body starts to generate streamers, the streamers can make contact with the separator under the circumstances. You can get struck by lightning if the windows are down. Okay, don't leave a gap during a lightning storm. Roll up the window so that the connection is completely severed. Right? So a side flash can hit you very easily if the windows are down.
Side flash bounced into his truck.
There's too much of a space there. There's too much of a gap. So the metal of the car is not going to be able to protect you if you have that much of a gap.
Hitting him in
roll up the window
neck and burning his head. The odds against Roy being struck a third time were over a quadrillion to 1. But only a year later, near his home, lightning hit a transformer and arced to his left shoulder. But this was not the end. In 1972, while taking refuge from a storm inside a mountain station, Roy Sullivan was singled out for a fourth time.
I recall Roy having lost all of his hair on his head. He also had a burn around his ankle that was, I would consider, substantial.
Morning, Rick. How are you, Roy? Pretty good. Working at Loft today? Sure am. Have a good one. You too.
By 1973, Roy had taken to carrying a bucket of water with him when he made his rounds, in case he caught fire again. Even though he tried outrunning the thunderstorms, in June 1976, Roy was struck again for a record 6th time. And his troubles weren't over yet. The following year, while out fishing, Roy was struck for the 7th time, and he became known as the human lightning rod.
People called him that before, human lightning conductor, but I don't know. I don't know if it was a chemical mineral in his body, but he said that before.
Roy was worried that metal on his body might be attracting the lightning.
He didn't even wear a wedding ring or a watch because of that. He didn't wear those.
Belt buckles and metal zips fuse and melt after a lightning strike, and many lightning survivors have terrible burns from metal objects that they were holding or wearing. But does metal on the body actually attract lightning? At a high-voltage lab in Manchester, England, researchers are preparing to find out.
We use an impulse generator, which is charged to a voltage of approximately 1.5 million volts, causing a simulated lightning bolt. Mannequins have been painted with an electrically conductive paint so that they simulate the resistance of the skin of a human under normal conditions.
Various metal objects have been attached to the test dummy on the left to see if it will be struck by lightning more times than the one on the right.
So she's the one who's wearing the jewelry. Same height, so height's not a factor. All right, so takes the first head. He takes the second head. Third one. And finally, she gets hit. And look at his reaction. Assume that he's got some metal if I'm so.
In this test, the dummy without metal was actually struck more often than the one with metal. Just like a real lightning strike, the electrical flashover has left telltale fractal patterns on the dummy's body. If Roy Sullivan did have any metal on his body, it should have had no effect. Lightning experts believe it was due to a combination of high exposure and bad luck.
All right, so metal on your body, does it attract lightning? All right, so based upon this result, the answer is going to be no. But the next question is about the size of the metal. Does it matter?
Maybe even more metal. Of course, if your tongue piercing is this big, lightning is the least of your worries.
I saw it go into the top of the head and go out to the bolt and back in.
It just goes to show, don't put any really big bolts in their mouth during a thunderstorm.
Finally, a test for the mother of all studs.
Oh, cheek piercing there.
It's unlikely to catch on at many nightclubs, though it might just help you get in the door. Will it attract lightning? At last, a direct hit.
Well, that knocked the doorknob right out of his face.
All right, so all of a sudden you're watching this. It almost created the impression that the size of the metal is going to matter, right? In reality, it's not the size of the metal, it's the shape of the metal that matters. Okay, so anything with sharp edges and pointing edges, it's going to have a higher charge concentration. So which means the charge density is going to be larger. As a result, the strength of the electric field is going to be larger. All right, that's the reason why we have lightning rods, and notice that they're extremely pointy, extremely sharp. Okay, so which means, number one, they become polarized, and then immediately they will become polarized. On top of that, around the sharp edges, the charge density is getting much larger, so they become very attractive to lightning. And then the whole idea is lightning hits it and takes it to the ground so that the building is. So that's the way it is. Okay, so here's a lightning rod, and that's the design. All right, so this design is Franklin's design. All right, Franklin came up with that design, and King George III said, okay, decided to come up with a different design. His design was a spherical ball, per se. Franklin's design works because it attracts lightning to itself. And if you have a spherical design, the charge distribution is going to be uniform. It's not as attractive to lightning. In fact, if you want to have a metal sphere, it's actually going to not attracting lightning. That's the reason why if you look at your car antenna on top of it, but you have a small ball, so that you try to prevent the car from getting hit by lightning. You don't want that to act like a lightning rod. All right, so German military helmet, World War I. Notice that they had those spikes, and Germans are pretty smart. So what happens if there's a lightning storm? Next thing you know, you're missing half the troops, and then World War II, you keep the helmet. The metal piece itself is not attracting lightning. They just got rid of the spike. Okay, so that was the difference. All right, so that's pretty much it. Okay, so we talked about
in the
best
middle of a
places to
children's
be.
soccer game, the skies open.
Okay, one last thing. We're going a couple of minutes over time, but that's fine.
Players take shelter under a tree, and the coach puts up a large umbrella. It's a terrible mistake. 17 people feel the force of the lightning strike. But how could so many have been hit by a single bolt?
All right, a lot of people survive.
Most victims
because most people, these are not direct hits most of the time.
are not hit by lightning
Number one, this umbrellas.
directly, but by a charge that jumps from a nearby object, such as a tree. This
Top of the umbrella is a little bit too sharp, pointy, so they got rid of the pointy edges on purpose. So it was kind of attractive.
side flash still has enough
So most people get hit by a side flash, so
power to stop the heart and burn the skin.
that's usually survival. The next thing that happens, the ground becomes electrified. As a result, you will get shocked.
Victims can also be shocked from below. Immediately
All right, so the best thing to do, just remember,
after a strike,
you get caught outside.
the ground
Don't lie down on the ground because the ground is going to become electrified. So that's one of the best ways you can get yourself
becomes
killed.
electrified. The current
Keep your legs together, and there's a reason for it, as you will find out next week. Or
travels through the person where they make contact with the ground, usually up
if there's too much space between the legs, the current is going to go up one leg, come down the other.
one leg
If you're a guy, you may end up having roasted nuts.
and down the other.
If you're caught out of doors in a thunderstorm, the best thing to do is get indoors in a sizable building. If you can't do that, you should get into a metal car.
The car's metal body discharges the current away from the driver and below.
All right, I'm just going to kind of disagree with him. The sizable building versus a car, which one is better? He thought that the sizable building is better.
Never stand under the tallest tree. Try to stay off hills where you're the tallest object.
But you're not totally safe
All right, guys, I don't care how big the building is, or how sizable the building is. You got problems in these buildings. All right, if the lightning misses the lightning rod, it's going to hit the building. All right, the frame of the building is metal, so which means that the entire building is going to become electrified.
Indoors, you shouldn't touch anything that's connected to the outside.
So which means that you can't be touching anything connected to the outside in that
Because the
building.
lightning could strike that outside and come in, and that includes the telephones with
Don't be on the phone.
wires. Shouldn't be leaning against the refrigerator.
Don't be getting anything from the fridge.
Shouldn't be near the house plumbing.
Don't be pissing or crapping.
Shouldn't be in the shower.
Don't be in the shower.
Just stay away from everything.
Stay away from everything. All right, you don't have those limitations inside the car. You can piss and crap in your car. It's still going to be fine.